Okay, so today we are starting with some trig, of course, because we're doing trig for the next, several units. And that very first trig problem, I would not expect you to know how to do yet, but we're going to teach you how to do that kind today, where you do substitutions. Let me ask this. I bet some of you could say that tangent is actually equal to something. It's y over x. But since y is really which one? Sine. Over x is really which one? Do you get tangent is really sine over cosine? And I can swap that out, and tangent is gone, but sine over cosine is there. And do you get then that I can do a little bit of flipping and multiplying, where because I'm dividing by sine over 1, and I can flip and multiply, and then I can get my sines to cancel? Anyway, that's the type of thing that we're going to do today, is swap things out. All right, so I'm not saying I'm just showing you the answer to all of the ACT. It's just ACT has trig on it. There's 4 trig questions on an ACT test. According to their rules, there can't be more than 4. But there will be 4 of the hardest ones. But for you, because you've just done trig right now, if you go to the ACT test, that's going to be the stuff that's actually fresh in your mind. You'll be like, it's problem 58 out of 60, and yet you know it. Boom, because, hey, we just did trig. So that's one of the reasons why you don't want to think the ACT is always about the hard problems are at the end. For you, if you just did this today and you went and took the ACT, one of the last questions might be trig one that'll be like, just did that in class, easy. Okay, so look at 2 here, and somebody tell me a way to start this thing. Yes, sir. You're going to say that x equals 1. Interesting. 1, 1, and 1. And then that's going to turn this into 3 plus 3 plus 3, which would equal 9. Okay, then I could go down here and see if any of these other ones would result in something that would give me 9 if x equaled 1. That's a really good idea. So then this one would give me 1, or so it would give me 9. So it could be that one. This one would give me 9, so it could be that one. This one, 3 to the 3rd, that'd be 27, so it can't be that one. This one would give me 3 to the 1, which is 3, so it can't be that one. And this one would work too. Oh, not D. I screwed up on something on D. Oh, 9 to the 3rd. Yeah, 9 to the 3rd is definitely not 9. Can't be that one. But it could be this one or this one. Cool. You got it down to 2 with that technique. It's either A or it's E. All right, so let's approach from a little different way. Would you agree that there's 3 of the exact same thing? Isn't that 3 times that thing? Instead of adding them up, 3 times that thing. So 3 times 3 to the x. Okay. Now, would you agree this 3 would have a power of 1 on it? Now, do you get that when you have problems like a to the 2nd times a to the 5th that you'd add the powers? So, which one is it? A or D? Okay, it's 3 to the 1 plus x, or x plus 1. All right, I know I was a stretch, and it stretched me the first time I saw it too. That was not an easy one. I thought, man, this one's actually really confusing me, but all right, and then this last one involves common denominators. You can't really add these two because they don't have a common denominator, but you can always make it have a common denominator if you want to. It has a denominator here of 3 over 1 is 3, and that could be changed to multiplied by x on the top and x on the bottom. 3x over x is the same thing as 3, isn't it? And then they've got a common denominator, and you can add them, etc. So I don't want to waste any more time on these, but I wanted to show you this is where what we're doing right now kind of intersects with the ACT. All right, so let's move on. Is this always true? No. Is it sometimes true? Yes. If I make x equal 1, then it'll be true. But if I make x equal 3, then it won't be true. How about this? Will this always be true? And I know you're careful about saying always, but this is, if you're smart, it's often a trick when they say always or never. Okay, but if x isn't equal to x, we have trouble. So this is a true statement. Okay, because if I make x be 5, then it'll be 5 on both sides. All right, how about this? Is this always true? No. Is it sometimes true? Yes. All right. Give me an angle where it would be, and I told you to memorize this. Sine of 30. Very good. Also known as pi over 6. Okay. So wasn't there another place that sine was equal to a half? Remember how sine equaling a half is, oh, students, take calc. Sine is in 2 spots. So you get that this is 30 and then it's 30 here. And so some kids forgot that there isn't just 30. It's 30 plus the other one, 150. There's 2 of them that work. But is this always true? No, because if I put in 31 degrees, sine of 31 is definitely not a half. It's sine of 30 that's a half. So that's not always true. All right, what am I getting at? Well, this obviously is the same and therefore true. We want to get to a statement that's true. In today's homework, you're asked to prove that this side of the equation equals that side of the equation. If you do all this work, and you get from this side, and you get down to this kind of a statement, you get that what you have must have been truth because it led to a true statement. Okay, so that's what we want, is a statement like this at the very end. If we have a statement like sine of theta is equal to tangent squared minus 5, that might even be true sometimes, but it's not a true statement all the time. You have to have it come down to equal exactly the same thing on both sides. All right, so let me set this up by getting to this slide, and I want to do a quick reminder. Remember that this distance was x and this distance was y? So now I want to do a replacement. We just said a second ago that sine was y, right? So I'm going to say that y right there, I want you to write sine theta. Remember, just the word sine would mean nothing. Sine theta is an actual thing. It's a real thing. It's sine of some angle, and it will be a ratio when it's done. Okay, so instead of x, if sine is y, which one's x? Cosine. So put cosine of theta right there. And do you remember what the hypotenuse was in the unit circle? It's 1. You're thinking about tangent. Tangent is sine over cosine. All right, but for right now, there's my little triangle. It's got a sine and a cosine and a 1. Would you agree it's a right triangle? What are some things we know about right triangles? There's a right angle. The other 2 angles add up to 90. What else? A squared plus b squared equals c squared. And therefore, what's true in this one? One squared, which is 1, right? Write that down. That's the first of many identities, they're called. Now, I want you to you're going to be going back and forth between 2 documents today. What I need you to do now is make up a nice new Notability doc and call it Trig Identities. Go make a new one right now. I know you could use a blank page in this, but then you'd never be able to find it again. We want a document we can use and add to it each day. I'm going to be teaching a few more each day. So you're going to call this Trig Identities. And the trig identities are statements of fact that you can count on. I just showed you why that was true. It is always true that sine squared theta plus cosine squared theta is equal to 1. I know some of this squared thing is bothering some of you, so I'm going to talk about it for a second. Some of you would have wanted me to do it this way. That is the exact same thing. It's just a shorthand to write it where you put the squared here. Do you get why you wouldn't want to put the squared on the theta? Because then the angle would be being squared. And that's not what we want. We want the whole thing to be squared. So if you're writing it this way, I'm actually okay with you writing them that way. It's just going to cause you to have to write parentheses every single time. It's just faster. Approved shorthand is to say that. Cosine squared theta equals 1 squared, of course, is just 1. All right, so you're making this blank new notability doc, right? And I want you to give that one that you just wrote, it's special. It is called a Pythagorean identity. I'm going to pause for a second while I pull up a sheet. All right, we've got one fact. Sine squared plus cosine squared is equal to 1, and we're going to write that on a separate sheet. I'll show you that sheet for people that are following the video here at home. I'll show you that at the end. All right, now another Pythagorean identity needs more of the functions like cosine and tangent and secant and cosecant and all that stuff. So I'm going to show you where they are in our picture. I mentioned tangent. Extend this line out a little bit. Do you agree that a tangent line touches the circle only once? You may remember that from geometry, you may not. You can trust me now. A tangent line is a line that will touch the circle exactly once. I feel like I was slightly off, and then I'm going to try one more time. Because when I'm done with this, this line should make a right angle right here. Think about the geometry of that. I got a circle, and I got the radius going out, and when I have this point that touches that spot, the spot where the radius touches, it should touch it just perfectly once so that you make a right triangle right there. Okay, now I said it was the tangent line, and it is. It's made up of, from here to here, can be visually represented as tangent. And from here to here can be visually represented as, take a wild guess, cotangent. Now, there's 4 of my functions on this picture. I just need 2 more. Does anybody want to nominate a function that they want to see where it is? Secant. Where is secant? All right. Secant is this one that goes from here to here on the bottom of that triangle right there. And it is made up of cosine plus a little bit more. Remember, cosine only went to there, right? So the whole thing is called secant. And what's one more function? The only function we haven't mentioned yet. Cosecant. And that goes along here. So, does anybody see another right triangle that should yield another true statement using Pythagorean? I'll give you a hint. I want you to have a 1 in it again because that's a nice number. You get 1s a lot when you're reducing things, and so if you can have a 1 in it, that's the best kind of Pythagorean. Somebody mentioned this last hour, I want to point it out, and it's true, and it's kind of cool. That squared plus that squared would equal that squared. But that's really a complicated one, and not something that you would use in a typical homework question, but it's true. This is another one that's a little simpler than that, and would give us another Pythagorean statement. Yes, sir? 1 plus, and I'm saying 1 squared is just 1, right? Plus cotangent squared. That's right. If you look at the picture that has this triangle here, I'll try to call it out for you with the screen. That and that and that. Can you see why 1 squared plus cotangent squared would be cosecant squared? Now that's really hard to remember, but we're from Minnesota. Would you agree that the one with the coat is cozy. Dumb little statement, but fun way to remember it. One with the coat is cozy. Okay? This is one more that involves a 1 and different functions. We've used 4 of our functions. Yes, sir. I'm going to go 1 plus tangent, just because it'll make a snappy saying later. Yes, sir. And that's this triangle here I'll make with the blue bars. You get how 1 squared plus tangent squared would be secant squared. And, keep me from rambling on about sunscreen now, but the one with the tan is what we seek, at least at the beach. Go ahead. The one with the tan is what we seek. Okay. So now, you have 3 of these powerful Pythagorean identities. You get that if you were doing this problem and it had this in it, and you were asked to prove that that was equal to 1, that would be a typical easy proof. Then I'd have to swap some things out. I'd have to go like, okay, I can take this out and put in something else. Like, I know sine is 1 over its flippin' sister. You remember that one? What's the sister one of sine? Cosecant. So it'd be 1 over cosecant. But hint, that wouldn't have helped. I could pull out cosine and put in something else, like 1 over its flippin' sister, which, what's this flippin' sister, or the reciprocal function? Secant. So I could put 1 over secant. Ooh, that sounds like it has some potential if this was cosecant up here, but you really struggle with these at first until you see something, and then you go, oh, that makes it so obvious. Did you see something? Okay, hold that thought a second. I know some people did not catch that. If you solve this for what? If you get the sine squared alone, do you get that you would put that over to the other side and you'd subtract cosine squared over there and you'd have 1 minus cosine squared? I'm going to say that again. Sine squared. After I subtract cosine squared from both sides, this would cancel this, and sine squared would equal 1 minus cosine squared. Cool. So that means in your proofs you could say, well, sine squared comes out, and 1 minus cosine squared goes in. And now isn't it really obvious that it equals 1? The final answer always has to be a true statement. Do you remember me showing you that a true statement always has to be the same exact thing equals the same exact thing, 2 identical things? So I'd have to finish this by saying this simplifies to 1 equals, that is 1, and there I've got a true statement. If you end with a true statement, I know you've proved it. All right, so now let's get that list up now of the whole rest of them that are ones you can count on, and you need to memorize this. For this next test that we do, you are going to need to be able to memorize because we have a ton of stuff to know. Hold on. There we go. The most important one is circled up there. Sine squared plus cosine squared is equal to 1. But the other ones, they have snappy sayings. The one with the coat is cozy. The one with the can is what we seek. The reciprocal functions, those are the flippin' sisters. Sine is 1 over cosecant. Cosine is 1 over secant. You should write this down. Remember that sheet I told you to make? You will hate yourself later if you don't have one place with all of your functions on it. If you have to look them up on separate assignments, oh, it's awful. You want to get it all on one sheet. If you have to, make up some flashcards and memorize these puppies. Because you need to know these like the back of your hand, because we're going to be using derivatives of them. Like, for instance, you know this sine squared plus cosine squared equals 1? You got to be able to say, well, because I know that, then I know that sine squared must equal 1 minus cosine squared. You do not need to write this out, but you need to be able to solve it for anything. You get I could solve out of these Pythagoreans for anything. Let's say I wanted to solve for tangent squared. Sure, just subtract 1 from both sides. And I got tangent squared to be secant squared minus 1. But I'm not asking you to write out all the possible permutations and combinations and memorize that. That's crazy. These are the ones that they really kind of boil down to. So, if a problem today has cotangent in it, do you get that I can say, well, I'm going to pull out cotangent and put in cosine over sine, because they're equal to each other. So wherever I see cotangent, I can put cosine over sine. I'm going to pause for a second. Okay, got to clean back up again. So here's my list. These are sometimes called the quotients, because you get quotient means divide, and that divided by that, and that divided by that are quotients of each other. Oops. Hold on, got to click the pen. So sometimes those are called the quotient identities. All right. Have you had time to copy those yet? You can always ask the kid next to you if you need to. I need to drag these back over to my other board. Pause what I do. All right, so let's actually look at some advice on how to do these kinds of problems. But first, just like see a problem. Here is a couple problems that are worked all the way out. Right here would have been the original problem. And do you notice that only one side changed here? Sine, it stayed the same the whole way. The right side was left alone. You don't have to always leave the right side alone, but you have to leave one of the two sides alone. When you're proving something, to be a mathematical proof, you can't have tweaked both sides until they were equal. You can only tweak one side, do manipulations on that one side until it finally equals the other side. But notice how they end. They always end with a true statement like tangent equals tangent. That's how you know you're really done. I know right here you could say, but you told us that tangent equals sine over cosine. Yeah, that's true. So you only have one step left. Change your sine over cosine into tangent. And if you don't end with tangent equals tangent, you didn't prove it. Okay, so let's look at some of the swaps they made. Do you see that they replaced cosecant with 1 over sine? Isn't that on our list somewhere? Well, wait a minute. Sine is 1 over cosecant, but they'll go back and forth. The flippant sisters are the flip of each other. So do you get what I mean? On our reciprocals list, we had sine, cosine, and tangent. But that means they also go backwards. So let me ask you, what's cotangent? 1 over tangent. What's secant? 1 over cosine. What's cosecant? 1 over sine. Okay. Now, I wasn't saying the squared ones. All right, so let's move on. The other side here, they replaced secant with 1 over cosine. And then when you multiply this, you get sine over cosine. And then they just had one more step, change sine over cosine into tangent. And now tangent equals tangent. And now it's proven. That is a typical problem. Notice how they start manipulating the complicated side. They leave the other side alone. And they end once you've got the two things being exactly equal. All right, so now let's find some advice. These are really good strategies. I'm going to say them quickly because right now it's like me explaining the finer points of picking a lock. If you don't know how to pick a lock at all, and I tell you that, oh, this was a really important part where you stick the thing in and you feel the tumbler, you're like, I don't even know what you're talking about because you haven't even done one yet. But let me just tell you, this is a really good list for later once you're good at these. These are some of the really important, for the higher level, more complicated ones. Come back to this list because it's a great list. I told you a couple already. Start on the more complicated side. Use the identities. Notice this says obtain common denominators. Remember me making you do common denominators on the top 20? On the top 20, you had to do common denominators a lot, right? That's why I had you do common denominators in the top 20, because I knew this day was coming, and if I had to try to teach you how to do common denominators at the same time as teaching really complicated trig, it wouldn't work. That's why I hope you've already got your top 20 mastered. If you don't, you need to come in and get that mastered, because these kind of things are coming up left and right. Next one, the Pythagorean identities. Those are the ones I just taught you a second ago. But there's some more detail in here that you're not ready for yet. Differences in sums of squares. We'll talk more about that when you're more advanced. And another thing is conjugates. I'll just tell you this about a conjugate. What do you think the conjugate to 1 plus x is? The way I said that should give you a hint. Okay, so you don't know what a conjugate is, but you will in 2 seconds. The conjugate to 1 plus x is 1 minus x. And what happens is you can FOIL it out and you get 1 minus x squared. Does that sound like a little bit like 1 minus sine squared? Let's see how that could come in handy in trig. I know this is like the fine points, complicated stuff you're not ready for yet, but this list is really good. Last thing that you can be ready for is this. If you get stuck working on the one side, you can always work on the other. You don't have to take the more complicated side and manipulate it. You can manipulate either side. You just can't do both. You got to do either one side or the other. So if you try the one side, it doesn't work, erase it all, start over again, and try taking the other side, manipulating it. All right, let's look at a couple problems. Here's the first one I want to do for practice. So, I know it's kind of warm in here. I opened the door. Hope that helps cool it off and keep you from having a hard time staying awake. I'm sure it can't be that what I'm telling you is boring. Couldn't be that. All right, so of these two, obviously that's a more complicated side. Can you tell me something I could swap out? I can take this out and I can put that in. Which one's 1 over cosine? Secant is 1 over cosine. I agree, and there was another way to do it too, but I'm going to start with that way. Secant is 1 over cosine. And then I'm going to bring this straight down. These arrows are like gold. You need to show me what you did with the little arrows. Now, I will let you get away with less arrows. If you didn't change it at all, like cosine, you don't have to tell me that that cosine goes to that cosine. But if you change something, like I changed secant into something else, draw me an arrow and show me I changed secant into 1 over cosine. Now, why can't you just say that equals 1? Because I can see that that's going to equal 1. You got to do one little step at a time until it is 1 equals 1. That's how I have to end. So, yes, you can do some canceling, but first I'm going to put them on top of each other. Cosine theta over cosine theta equals 1. And then, that is as far as I can go without actually changing it. 1 equals 1. There. Done with the first one. That was, of course, a really easy one. We had to only make really one swap. Yes, sir? I'm not going to make you say proven at the end. Even I will know that if you got the same exact thing on both sides, you have proven it. Okay. On the other side, can you see anything that we could swap out? There's a lot of things. Let's say I want to work on this side. Do I have to work on the left side? No, I can work on the right side. What's cosecant the same as? 1 over sine. What's cotangent the same as? Cosine over sine. Now, can you see that when I multiply that out, what do I have on the bottom? And isn't that what I wanted to have on the bottom? So now I've got 1 times cosine is cosine over sine squared. And that's what I wanted. Cool, I just bring it down. Okay. Now that I've got a statement where I didn't mess with the left side, but I did mess with the right side until they were equal. If I only mess with one side and I get down to the exact same thing on both sides, I did it right. That's proving. Okay, those were, of course, easy ones, and it's going to get more complicated. So let's get into some of the homework for today. I'll pause while we find. Okay, so here's our first one. Why is that puppy particularly adorable? A little heart on its back. Can you imagine having a little birthmark that looks exactly like a heart? It's awesome. Anyway, if I'm looking at this to me seems like the more complicated side, so it seems like a no-brainer. I should probably mess with that side. And if I can't make it work, I can always go back and do the other side. But I see something. Does anybody else see something? Okay, I think you see that this kind of looks like this. But it's not exactly the same as that. So I can't like swap it out directly for that, of course. Can I make it so that something is exactly the same as that? I take this identity and I subtract cosine squared from both sides. You get, I now have 1 minus cosine is equal to sine. Did I do that wrong? Sine squared. Did I do something wrong here? I think I did it right. Oh, I just didn't say squared. Okay. There's a squared right here. All right. So I'm going to put, see, here's 1 minus cosine. I'm going to put in sine squared for that. So notice if it doesn't change, I can leave it alone. But if I change something, I got to draw an arrow and say, here's what I changed, Mr. Server. 1 minus cosine squared, that's equal to sine squared. Now again, somebody who really knows what they're doing is going to say, well, that's equal to cosecant. I can tell. You can't just say that's equal to cosecant. But what could you do to simplify it a little bit more? Yes, sir? How about this? We're going to keep this the same, right? How about this? Would you agree that one step before what you said would be to say this? Now what did I do? I changed my sine squared into sine times sine. Now tell me what you said again. Do you see why it's 1 over sine now? Because these can cancel. So now it's 1 over sine. And can I just write cosecant right now? No. If you end like this and you haven't got the same thing on both sides, I will mark it wrong. Just have to go one more step, though. That is cosecant. So I go cosecant equals cosecant. There. Now that it says the same thing on both sides, you've proven that it was true. All right. Did your first one with you. The rest of them are yours. There's only 3 more. The one on this page, and then there's another page that's got a couple more. Now, the one on the right-hand page is easy enough. A lot of kids finish it in class. There's our 12-minute warning. I want to give you one hint on number 98. Take a look at that one. Because you especially want my hints right now because we're not posting answers for this unit. You might be thinking, these are really hard. I wanted to look at the answers. I know. But there's only 4 questions. And if you get used to seeing, well, I just need to know the first step. I know. Because as soon as we tell you the first step, the rest of it becomes totally obvious and super easy. You need to get that these are really hard, and you're going to fake yourself. We did post the answers at one point. And the kids thought they were doing fine. They just got to the test and failed. Not everybody, but most of the kids just failed because they weren't used to struggling with these and going, I don't know what to do. See, these aren't exactly like the ones we just did a second ago. Who sees something in this, in number 98 right here, who sees something in that that's got potential, even if you're not sure what to do with it? Yes?
Never mind, I don't know.
It's okay. It's okay. What do you see? Oh, that's true? If we could make this somehow be a what? A 1, then it would be true, because 9 minus 1 would be 8. But that's not one of our identities. Cosine squared minus sine squared isn't equal to 1. Or is it? Let me give you a hint. What's my favorite saying that often solves really complicated things and is the answer almost every time? If you can factor it, you should. It comes to the rescue again. You mean factor. You can just simply factor out something and it will be cosine squared plus sine squared, or sine squared plus cosine squared. All right, leaving it at that. Hopefully you can figure that one out. And then number 102, I also think factoring is going to come in handy there, although it's a little more obscure about why. Now, if you can't figure it out by manipulating the right side, then, try the left side. But I think I'd start with that right side. And somehow do some swapping so that you can factor something. All right. I want you to get that these are tricky. If I just post the answers, you will have said, that stuff was easy, when it's totally not easy. And you need to respect this next test. It's going to be one of the hardest tests. Because it's really not clear what to do. There's not like, other stuff we do is like, first you do this, then you do that, then you do this, then you do that. Here you have to, I'm not sure what I should do first. You have to struggle with that. Yes, sir?
So if you pretty much like solve it, it's
Coming up on the end here, so I'm going to stop the video at this point. I think that's all I have for you for today.